Hi, this is Satyanarayanan from School of Electronics Engineering, VIT, Chennai campus. In this video lecture, we will cover cross correlation and autocorrelation with solved examples. So first, we will quickly go through the definition for correlation and the definitions for two types of correlation, cross correlation and autocorrelation. Then we will see each type in detail. So the suggested reading for the contents covered in this video lecture is the book Signals and Systems by Alan V. Oppenheim. First, let us see the definition for correlation or the correlation function. The correlation function between two signals is a function of the amount of shift. So we will be in a better shape to understand this definition by the end of this lecture. In other words, after solving some examples in cross correlation and autocorrelation, we would be in a better shape to understand this definition. So for time being, let's move on to the two types of correlation function. First is the cross correlation function. It is the correlation between two different signals. That's why the name cross correlation. The other one is autocorrelation, which means the correlation of a signal with itself. So in applications like radar, where you send a signal and receive an echo of it, then the cross correlation plays an important role in detection. First, cross correlation function. Let's see the mathematical definitions. And the definitions of cross correlation varies depending on the type of the signals. So for example, for energy type signals, x of t and y of t, or basically here it is x of t and y of t stand for continuous time energy type signals, and the x of n and y of n pair stand for the discrete time energy type signals. So let's just see the cross correlation function between the two continuous time energy type signals. So this the cross correlation is denoted as rxy of tau, so is equal to the integral minus infinity to infinity x of t y conjugate of t plus tau. So t plus tau stands for a shift by tau, and this, the conjugate symbol is to denote the complex conjugate of y of t plus tau. This is in the case of continuous time signal. In case x and y are discrete time signals, they are denoted as x of n and y of n. Then the cross correlation function between x and y is denoted as rxy of m is equal to summation n equal to minus infinity to infinity x of n times y conjugate of n plus m. So here the variable m is used, and so depending upon the type of the signal, if it is continuous time there will be an integral, if it is discrete time there will be summation. So this is for energy type signals. So as I mentioned already, y star represents the conjugation, complex conjugation. For power type signals, again, first for the correlation between the cross correlation between two continuous time power type signals x of t and y of t is expressed as rxy of tau is equal to limit t tends to infinity 1 divided by t integral minus t by 2 to t by 2 x of t y complex conjugate of t plus tau dt. And in the case of discrete time signals x of n and y of n, that is discrete time power type signals x of n and y of n, the cross correlation is expressed as rxy of m limit k tends to infinity 1 divided by 2k plus 1 summation n equal to minus k to k x of n times y star of n plus m, that is y conjugate of n plus m. Here it is 1 divided by 2k plus 1 because from n equal to minus k to k there are 2k plus 1 discrete values for n, basically 2k plus 1 values for n. Okay. So let's see the first example. So find the cross correlation function between the two signals. X of t is exponential of j 2 pi f naught t and y of t is equal to exponential j 4 pi f naught t. So these two signals are complex sinusoids or complex exponential signals. And the first signal is of frequency f naught and the second signal, if it is written as exponential of j 2 pi 2 f naught t, then it is evident that the second signal's frequency is 2 f naught. So basically we are trying to find the cross correlation between two complex sinusoids of different frequencies, one with frequency f naught and another with frequency 2 f naught. And being complex sinusoids, these are power type signals. Therefore, and they x of t, it is denoted as x of t and y of t. So they are power type continuous time signals. So therefore, we should pick the correct definition for Rx of Rxy. So therefore, the Rxy of tau is equal to limit t tends to infinity 1 divided by t integral minus t by 2 to t by 2 x of t y complex conjugate of t plus tau. So then this step is mere substitution of x of t and y of t values. So first is x of t. In the place of x of t, we have exponential of j 2 pi f naught t. So in the place of y of t plus tau, should be exponential of j 4 pi f naught t plus tau. Owing to this complex conjugation, there is a minus sign here. So next, we can write this exponential of minus j 4 pi f naught t plus tau dt, sorry, t plus tau as two terms, as the product of two terms, exponential minus j 4 pi f naught t and exponential minus j 4 pi f naught tau. So the integral here is on t, therefore the exponential minus j 4 pi f naught tau term can be treated as a constant and hence taken out of the integral. So therefore the term comes first, then times limit t tends to infinity 1 divided by t integral minus t by 2 to t by 2, and of course the remaining two terms can be combined. So when added, it results in exponential minus j 2 pi f naught t dt. Yes, so the constant term taken outside, remaining two terms combined. So now we are left with integral minus t by 2 to t by 2 exponential minus j 2 pi f naught t, and using Euler's theorem or the Euler's formula, the exponential minus j 2 pi f naught t can be written as cos j 2 pi f naught t minus sin j 2 pi f naught t. So therefore they can be written as two exponentials. So one exponential, sorry, two integrals, two different integrals, one for the cos term and other for the sine term. Yes. So the product or the rxy is 0. How we get 0 is, so here there are two integrals. First there is an integral on a cos. So what happens is, integral is basically area under the curve. Just visualize a cos theta curve. So what happens is, if you draw a cos curve, then oh okay, so here there shouldn't be this j coming in, so it's by mistake, so you can just ignore this j inside. So this is basically integral over minus t by 2 to t by 2 cos 2 pi f naught t dt minus j integral minus t by 2 to t by 2 sine 2 pi f naught t. So here, so when you take integral cos, when you evaluate the integral cos 2 pi f naught t dt, it means you are trying to find the total area under a cosine curve. So when the limit is between minus t by 2 to t by 2, the total area will be 0, because there will be equal positive and negative regions. So they will cancel out and results in 0. Even we can show mathematically that this integral will be 0. On the other hand, for sine, when any symmetric interval for sine will any symmetric integral for sine will result in a 0 value. So therefore both integrals become 0, and hence the entire term becomes 0. So therefore the exponential minus j 4 pi f naught tau multiplied with 0, it will give 0 as answer. Therefore the cross correlation between two complex sinusoids of different frequencies will always be 0, regardless of what the frequencies are. This implies x of t and y of t are uncorrelated, and hence they are orthogonal to each other. Therefore, if you want to show that two signals are orthogonal, or to verify whether two signals are orthogonal, then the first step is to evaluate the cross correlation between the two signals. If it is 0, then they are uncorrelated and they are orthogonal to each other. So next we will move on to autocorrelation. So autocorrelation function, okay. So autocorrelation function is the correlation of a function or signal with itself. So therefore, it's in the cross correlation we had x and y. So here they both x and y are same, so we can just replace y in the cross correlation formulas with x. So therefore for energy type x of t or x of n, for energy type signal x of t, the autocorrelation will be minus infinity to infinity x of t x conjugate of t plus tau dt. Then for discrete time energy type signal x of n, the autocorrelation is rxx of m is equal to summation n equal to minus infinity to infinity x of n x conjugate of n plus m. So again, it's x conjugate means it's a complex conjugate. So therefore, for similarly for a power type signal x of t or x of n, so the autocorrelation formula or as follows. Okay, this is a one special feature of autocorrelation. So for signals, be it discrete time signal or continuous time signal, you can evaluate its energy or power using the energy power formulas. If in case you are given with the autocorrelation of a signal of a continuous time or discrete time energy type or power type signal, you can easily obtain its energy or power. So how to do that? For an energy type signal x of t or x of n, so the energies are computed as follows. For a continuous time signal x of t, if you have its autocorrelation rxx of tau in hand, then just substitute tau equal to 0. Therefore, you will get the energy of the signal. Similarly, in the case of discrete time signal x of n, then you just put, in the case of discrete time signals, it will be the autocorrelation will be rxx of m, and substituting m equal to 0 will give the energy. Similarly, for power, you would have obtained rxx of tau, power type signal x of t, you would have obtained rxx of tau, then substituting tau equal to 0 will give the power of x of t. In the case of discrete time signal x of n, substituting m equal to 0 in the autocorrelation expression rxx of m will give the power of x of n. So autocorrelation has certain properties. First is the peak value of the autocorrelation always occur at the zero shift. So be it continuous time signal or discrete time signal, the tau equal to 0 or m equal to 0 will have the maximum rxx of tau or rxx of m. For all other tau values or m values, the autocorrelation will be less compared to rxx of 0. So the autocorrelation is an even function. Means rxx of tau, say tau, a non-zero value for tau will be equal to rxx of minus tau. Similarly, for discrete time signals, rxx of m will be equal to rxx of minus m. Another important property of autocorrelation is a time shift in the signal does not change its autocorrelation function. In other words, the autocorrelation functions of x of t and x of t minus capital T are the same. So let me give an example. X of t equal to cos t or x of t equal to cos 2 pi f naught t will have the same autocorrelation as that of cos 2 pi f naught t minus 2. Next, we will see another example. Find the autocorrelation function and power of the sinusoidal signal x of t is equal to a sine 2 pi f naught t. We know that sinusoidal signals are power type signals. It is given as x of t is equal to, so which means this is a continuous time signal. So it is a continuous time power type signal. So if we use the appropriate autocorrelation function formula, we should be able to get a sine, we should be able to get the autocorrelation function for a sine 2 pi f naught t. Of course, finding power of the sinusoidal signal is very easy. In the autocorrelation expression, substitute tau equal to 0. Yes. Let's start solving it. So since x of t is a power type signal, r xx of tau is equal to limit t tends to infinity 1 by t integral minus t by 2 to t by 2 x of t times x complex conjugate of t plus tau dt. So just substitute a sine 2 pi f naught t in the place of x of t. The first term will be a sine 2 pi f naught t times the second term will be a sine 2 pi f naught t plus tau. Of course, the sine 2 pi f naught t is not a complex term, so this conjugation will not have any effect in the case of real values, real numbers. So sine 2 pi f naught t is not a complex, which means it does not have any imaginary part. So x conjugate of t plus tau is same as x of t plus tau. So it is sine 2 pi f naught t plus tau. Then there will be a here, so both the a's multiplied will result in a square times sine 2 pi f naught t times sine 2 pi f naught t plus tau. Okay, so this we are writing it using the trigonometric identity. Sin m times sin n is equal to 1 by 2 times cos m minus n minus cos m plus n. So once you put that, then you will get two terms. So a integral minus t by 2, okay, so there will be limit t tends to infinity 1 by t integral minus t by 2 to t by 2 a square by 2 times cos minus 2 pi f naught tau minus cos 2 pi f naught 2t plus tau. Of course, cos of minus theta is equal to cos theta. So, okay, so before that, we will just split this and write them as two integrals, summation of two integrals. So we have two integrals now. Then, of course, yes, cos minus 2 pi f naught tau can be taken outside the integral. So then the remaining will be minus integral minus t by 2 to t by 2 dt. And in the second interval, we are not disturbing it. We will just keep it as such, because we know very well when a cosine of something is integrated over a symmetric limit or integrated over the limits minus t by 2 to t by 2, this will result in 0. So this will result in 0. The first integral is quite straightforward. It is integral dt, so it will be just t upper limit t by 2 minus, oh sorry, upper limit t by 2 lower limit minus t by 2. So when added, then this integral value will be capital T. So now we have a t here and here, so we can just strike them off. So once we strike them off, then these two t's gets cancelled. Therefore the t is, there is no t remaining in this expression. Therefore the limit t tends to infinity carries no meaning, and hence it can be removed. So 2t gets cancelled, and therefore this limit term has no meaning and hence removed from the expression. So we will be left with a square by 2 times cos minus 2 pi f naught tau. Since cos of minus theta is equal to cos theta, we can write this as a square by 2 cos 2 pi f naught tau. Interestingly, even for a signal x of t equal to a cos 2 pi f naught t, the autocorrelation will be the same, a square by 2 cos 2 pi f naught tau. You can try it out. So let's move on to the next step in this problem, evaluating the power of the signal x of t. And we have our xx of tau as a square by 2 cos 2 pi f naught tau. So now we will put tau equal to 0 to obtain the power. So therefore it is a square by the power of the signal x of t is equal to a sine 2 pi f naught t is a square by 2. So then the next thing we'll be seeing is computing spectral density from autocorrelation. So consider a continuous time signal x of t. The spectral density of x of t and the autocorrelation function of x of t form a Fourier transform pair. In other words, you have the autocorrelation of a signal x of t, which is denoted as, let's say, rxx of tau. If you take Fourier transform on the signal, you will get the spectral density of x of t. So this result is known as Wiener-Khinchin theorem in probability. There are two types of spectral density. Again, it is dependent on the signal. So energy spectral density. Let's say your signal x of t is an energy type signal, then the spectral density of x of t is called energy spectral density. Therefore, the energy spectral density is equal to the Fourier transform of the autocorrelation of x of t. Next is power spectral density. So if your signal x of t is a power type signal, you will have rxx of tau autocorrelation. So if you take Fourier transform of rxx of tau, you will get the power spectral density of x of t. So for computing power spectral density or energy spectral density of x of t or x of n, appropriate definitions of correlation function should be used, and then upon obtaining the correlation function, we need to take Fourier transform of the correlation function. So thanks for watching the video. In case you have any queries, feel free to write an email to me.